delighted to have Salil Vadhan to give a plenary talk. So I guess you all know Salil, but he's a professor at Harvard University. He's done some amazing contributions to zero-knowledge proofs, complexity theory, cryptography, and in recent years, the privacy. He won the Gödel Award, and I guess I'm not going to bore you with a long list of all the awards, but perhaps a personal story that I got into interactive proofs and zero-knowledge proofs indirectly because of Salil. In the following sense, I was writing one of my first papers, and my PhD advisor at the time, Oded Bodai, he was screaming at me that this is really poorly written, and it's horrible, and I need to do it better. And I tried to improve, and it still didn't quite work. So eventually he told me, look, read anything by Salil, and that's the perfect example of clarity and crispness in exposition. And so I started, I read the thesis, I read quite a few papers, and along the way I also fell in love with zero-knowledge proofs and interactive proofs. So thanks, Salil, and I want to do that in the time.
Thank you, Tom. That's a very kind and generous introduction, and it's wonderful to be here in Warwick and to be here at CCC. It's been a few years since I've attended. Great to just see how the community is growing and evolving, all the new faces. And if it's any consolation, Oded probably didn't tell you that he also yelled at me when I wrote my first paper. So, okay, so what I want to do is give a survey of how over the last few years we collectively as a community have been getting a lot of mileage out of importing ideas from the algorithmic literature on spectral graph theory for the complexity theoretic problem of understanding the power of randomized space-bounded computation. So the plan is first I'll give a quick recap of kind of where we are, kind of the main sort of milestone results in about de-randomizing log space, refresh everyone's memory, and then give a kind of brief overview of spectral graph theory or the aspects of spectral graph theory that we'll be relying on at a very, very high level, and then survey some of the connections over the years between the two. And one of the things there, it'll be too long a list of results. I've tried to be reasonably comprehensive, that you shouldn't worry about coming away with understanding the specific results. The main thing I want to convey is kind of how much, again, mileage we seem to be getting out of this toolkit for problems that we're interested in. And then in the rest of the talk, I really want to focus on just a few ideas or techniques and their relevance to our problems in de-randomizing log space. So why Laplacians and inverting Laplacians are relevant for the problems that we are interested in particular, the role of error reduction techniques that we import from this algorithmic literature and the kind of mileage we've gotten out of that. And then a second piece, depending on how much time I have, is to talk a little bit about the different ways of measuring approximation and error that also are coming from this literature and proving to be useful for our problems, and try to say a little bit about where some directions and open problems are at the end. Okay, so let's start with this overview. Okay, so the main classes of interest are BPL, the log space analog of BPP. Oh, sorry, this is not one-sided error, sorry, two-sided error. Monte Carlo algorithms, bounded error, two-sided error, ones that always halt, and versus L, deterministic log space. And of course, our goal in the conjecture, just like we conjecture BPP equals P, we conjecture that BPL equals L. And there's a lot of conditional evidence to that end. But what we would really like to do is be able to prove this unconditionally. And some of the barriers that are there to proving BPP equals P unconditionally, like they implying circuit lower bounds by Cabinets and Pagliazzo and so on, don't exist in the space-bounded case. And indeed, there are very non-trivial de-randomization results. One highlight is Nissan's pseudorandom generator for space-bounded computation, which has a log squared in seed length. And then using Nissan, so this would only imply not a very interesting de-randomization of BPL, that BPL is in log squared space, which we know by, as I'll mention later, for non-de-randomization reasons. Sachs and Joe did use it to get a very non-trivial de-randomization of BPL in log to the 3 half space. So we'll use this L to the C notation to denote deterministic space log to the C of n. All right, and I want to stress we'll often be referring to both of these two settings. There's kind of the black box setting where you're using something like a pseudo-random generator to de-randomize. So we want where you don't get to look at the algorithm or the instance of the algorithm that you're trying to fool. You need to just generate pseudo-random bits or variants of that. And then the kind of white box setting where the Sachs-Joe algorithm falls in, where you actually look at the algorithm you're trying to de-randomize. And then another highlight is Reingold's theorem, which probably many of you are familiar with, that probably the most famous problem in BPL that was not known to be, it was shown to be in BPL in the late 1970s, not known to be in L until Reingold's theorem was undirect connectivity in undirected graphs. Right? Given undirected graphs, two vertices, is there a path between them, a walk between them? And then what I won't survey in detail is, these three highlights is kind of like summarizes our main state of knowledge about de-randomization of BPL. What have we been doing for the last 15 plus years? Well, there are lots of improved pseudo-random generators for restricted models of space-bounded computation, things that get, for example, O of log n or O tilde of log n seed length, and continual progress there that we hope will eventually lead to an improvement for the general case. So these are some of the models here, combinatorial rectangles, restrictions of various kinds of branching programs, and we'll see some of these in more detail later. Okay, so actually, why don't we actually get into the model? So changing terminology a little bit from what we usually use. I'm going to use this terminology that I'm pulling from a recent survey of Hatami and Hosa, which I think is better than our usual terminology. So we're looking at the non-uniform model corresponding space-bounded computations, are various forms of branching programs, but the ones that are relevant for de-randomization we'll call standard order branching programs, which means these are layered branching programs with n layers if you're looking at inputs of length n. And in the first layer, they read the first bit, the second layer, the second bit, and so on, last layer, the nth bit. So they are a special case of read once branching program. They read each input bit once in that they read the bits in consecutive order. Okay, and so they're even more specialized than oblivious read once. And we've been sloppy in the pseudo-randomness literature and sometimes just referring to these as read once branching programs. But I think we should be more careful. And so this is the models. We have some start state and an accept state, and you read the input bits in order. And we think of these as modeling the random bits of a randomized log space algorithm. Okay, and so we'll use W throughout the talk for the width of the program, which models the states of the computation, and n for the length corresponding to the input length, and a sort of canonical BPL or promised BPL, technically complete problem is estimating the acceptance probability of standard order branching programs, and the regime you're interested in there is the width is polynomially related to the length. Because space O of log n corresponds to poly n different possible configurations. So we're interested in the behavior of a standard order branching program. We're estimating it on uniformly random inputs. And Nissan's PRG is provides an approximation on pseudo-random bits, and the seed length I said before is log squared n. In general, writing all the parameters, it's really log n times log of nw over epsilon, whereas the optimal wouldn't have this extra log n factor in front, would just be log n w over epsilon. Yes?
When you add the standard ordered assumption, does it make it equivalent to streaming algorithm?
Yes, that's another way of thinking of it as a streaming algorithm. Yeah. And when people prove lower bounds on space of streaming algorithms, this is basically the model they're using. Thanks. So maybe we should call them streaming benching programs. Okay, so two restricted models. I mentioned restricted models earlier. One is that of a regular SOBP, where our out degree, if we think of this as a graph, always is 2 because you have a state you go to on reading 0 and reading 1. In a regular SOBP, we require that the in degree is also 2. Okay, so this first layer you see is not a regular layer because we have this as degree 3 and this is degree 1. This layer is a regular layer. The last layer is a regular layer. So in a regular SOBP, all the layers are supposed to be regular. One reason for interest in regular programs is actually they are as powerful as general standard order branching programs with some blow up in the width. So in the polynomial width regime, they're really equivalent. There's various forms of this, but just there's a new paper by Chin-Ho Lee, Ted Pine, and myself that shows really they can exactly simulate general standard order branching programs with a factor n, or actually n over 2 roughly, blow up in the width. And this means, in particular, if you have pseudorandom generators for regular SOBPs of polynomial width, you also get the general case of Nissan. However, if you restrict the width to say, let me be careful here. Okay, I realize there's an important caveat that'll come up a few times in the talk. This is if you allow many accept states. So for general standard order branching programs, it doesn't matter whether you allow one accept state or many accept states, because you can always merge things at the end. But you can't do that without violating regularity. So if you allow many accept states, then they can simulate general standard order branching programs. But with one accept state, they are weaker. They're also weaker if you're in the constant width regime. A further constraint on regular is you constrain the labeling so that the 0 edges alone make it regular, or a permutation at each layer, and the 1 edges make a permutation at each layer. So this last layer is a permutation layer. I think none of the, but if you look at this layer here, it's regular, but it's not a permutation layer because, say, these ones collide. And one way to think of permutation programs is as programs that are regular under all restrictions. If you do any restriction of some subset of the input bits, you're still left with a regular program on the remaining ones. That's equivalent to this permutation condition. All right, so now that was a very brief overview of kind of de-randomizing log space and our sort of target problems. And now let me turn to little overview of spectral graph theory. So what is spectral graph theory? It's kind of using linear algebra to understand graphs, and especially using eigenvectors and eigenvalues, though, as we'll see, they'll actually be kind of hidden, the eigenvectors and eigenvalues, for most of the talk, and then only near the end I'll kind of point out where they were hiding. In theoretical computer science, of course, we're very familiar. We all know and love expander graphs as one place where we use spectral properties of graphs throughout theoretical computer science and in complexity in particular. But the line of work that I want to talk about kind of importing ideas from, I think really started with this landmark paper of Spielman and Tang in 2004. That introduced the idea of spectral sparsification of graphs and used that as a building block to obtain nearly linear time randomized algorithms for solving Laplacian systems. So this class of linear systems, Lx equals b, where L is a matrix coming from a graph. This is the unnormalized Laplacian. You take the diagonal degree matrix minus the adjacency matrix. Throughout the talk, we'll actually be working with a normalized, or what I call a random walk Laplacian. L is identity minus W. So it's like basically hitting the unnormalized Laplacian with D inverse on the left. We will actually be carrying a lot. So Spielmann and Tung were for undirected Laplacian systems. And if you want to keep matrices symmetric, you would do what Itai mentioned in his talk, where instead of hitting with D inverse on the left, you would hit with D to the minus half on one side and D to the minus half on the other side. But for us, it'll be just nicer to talk about the random walk matrix. So this will be the Laplacians we'll look at. And one of the things that got us interested in trying to import ideas from this literature to de-randomizing space-bounded computation was this amazing sequence of works by Cohen et al. From 2016 to 18, which basically extended this theory of sparsification and nearly linear time Laplacian solvers to the directed case. First to Eulerian directed graphs that will come up later, where every vertex is the same in degree as out degree, and then eventually to general directed graphs. And we'd understood for some time that that was also the kind of barrier we were facing in de-randomizing of space-bounded computation. We had Reingold's algorithm that solved undirected ST connectivity in deterministic log space, and to go to de-randomizing BPL in general required somehow being able to handle general directed graphs. Okay, so now let me review this a little history of using spectral graph theory in this context of randomized space-bounded computation. Actually goes back to the very early days, the very first papers like of Gill that defined the complexity classes, where actually inverting Laplacians was used to prove that randomized log space is contained in log squared space, but not the BPL class that we are studying here, but PL, like the space analog of PP. So this is unbounded error randomized log space. So there's no gap between the yes and no, just above or below 50% acceptance probability, and even a non-halting version of that, whereas we restrict usually to the BPL where you're require that the algorithms always halt. But then somehow the Laplacians, I think that's the last occurrence for a long time that I know of Laplacians in the randomized space-bounded computation literature. But Sachs and Zhou did in their result take kind of a very sort of linear algebraic view of the problem of de-randomization, and they viewed it as a problem of powering stochastic matrices. And now this is powering up to like an additive error of like 1 over poly. So I'm just making this note here. I used the word exact there, so that's exact or to exponentially small error was in this earlier work on unbounded error. As you might guess, because if there's no gap in the probabilities, you'll need extremely high accuracy to distinguish yes and no instances. And throughout, whenever I talk about computational problems, I'm almost always allowing like a 1 over poly additive error, but I'm not going to keep repeating that throughout unless I explicitly am talking about the dependence on epsilon. Then Reingold also used linear algebra and more spectral properties quite explicitly in his algorithm for undirected ST connectivity, which works by taking an arbitrary undirected graph and in deterministic log space through a series of graph operations, turning it into a spectral expander while preserving the sort of ST connectivities, and then by gradually increasing the spectral gap. So eigenvalues playing a very explicit role in Reingold's algorithms, and then these successors where we were trying to push it to extend to directed graphs, and we were able to get some kind of extensions to regular directed graphs with an additional constraint of being what are called consistently labeled, some kind of oblivious de-randomization of those. The details won't matter so much. And then also similar kinds of like spectral expansion type properties were used in later pseudorandom generators with a O of log n bit seed as opposed to log squared as in Nissan for constant width permutation standard order branching programs through these works of Kautsky, Nimbarkar, and Pudlak and others that came a few years later. And just a remark, this consistent label condition is basically another way of viewing this permutation property in permutation programs. And then finally, there's this paper of Dean and Sarid and Tashma showing that actually another BPL complete problem is approximating to within additive error the second eigenvalue of stochastic matrices. So another thing sort of pointing to we really should be thinking about things linear algebraically and possibly also spectrally. All right, so now let me turn to kind of more this now recent line of work, which is really starting to connect to the algorithmic literature on inverting Laplacians. So first, paper of Dean, Lagal, and Amnon showed that actually you can invert, solve Laplacian systems or find inverses of Laplacians in BPL. And then using and modifying techniques from the algorithmic literature on Laplacian systems with Murtaugh, Reingold, and Sidford, we showed how to actually get a deterministic algorithm for solving undirected Laplacian systems or computing their inverses in nearly logarithmic space. So I'll use this L tilde for deterministic space O tilde of log n, like hiding log n factors. And then this was used to kind of solve some other problems on undirected graphs, spectral sparsification, approximating conductance of long random walks. And then we turned our attention to trying to take these results from the algorithmic literature for directed graphs and port them to the space-bounded world. And we got algorithms. We were able to do that also in deterministic nearly logarithmic space for kind of this graph theoretic natural problem of given an Eulerian directed graph. Again, this is a directed graph where every vertex is the same in degree as out degree. And you want to know what's the probability that a random walk of some length goes from one vertex to another to high accuracy, 1 over poly n error. We're able to do that, which a special case of it is estimating the acceptance probability of a possibly polynomial with regular standard order branching program in nearly logarithmic space. OK, so actually I made the comment earlier, if you can do regular branching programs of polynomial width, you could do general ones. That is if you can do it in the oblivious, like the black box setting, like with a pseudorandom generator. So that simulation, I said regular can simulate general with a factor envelope and width. That simulation is not one that we know how to carry out in log space, that we know how to do that conversion. This is an algorithm, so it requires that you actually have your hands on the regular branching program. And so you can't just apply that conversion. You'll pay more than log space at converting. On the other hand, if you had a pseudorandom generator that handles the regular case of polynomial width, you could get the general case because that doesn't require looking at the program. And so the conversion only happens in the analysis. OK, and then one other thing that another thing that came out from the kind of ideas that we developed in this paper is a new pseudorandom generator for permutation standard order branching programs. These are ones with the one accept vertex. And the interesting thing here is that they even work even for infinite or exponential with programs and still can have an O tilde of log n seed. And then there was a series of works giving improved what are called weighted pseudorandom generators for a variety of models. I'll talk about these, and I'll talk a little bit about what weighted pseudorandom generators are later, but roughly they are pseudorandom generators where you can kind of attach coefficients to the outputs, which can be positive or negative, and you can have kind of cancellations as you're estimating the acceptance probability of a branching program. And so a lot of progress on weighted pseudorandom generators coming out of importing ideas from this spectral graph theory literature. And then one application given by Hosa is actually to have the first improvement on the Sachs-Joe derandomization of EPL. So from log to the 3/2 to little o of log to 3/2, saving a square root log factor. Small savings, but still first improvement in nearly 30, over 25 years. And then another exciting result of Cohen, Duran, Sperlo, Tashma, and Putterman, and independently by Putterman and Pine, is derandomizing what I'd call medium width standard order branching programs. So these are not polynomial width, but they're much more than constant width in nearly log space as well. All right, great. So that was again, the point is not for you to take away all the specific results and the parameters, just to get the idea. We're getting a lot of mileage of a lot of different kinds from this using spectral graph theory. Any questions at this point? All right, so now let's talk about Laplacians and how they help us understand branching programs. Okay, so all right. I mean, as we're probably used to thinking of, we can think of branching programs kind of as graphs, as we've drawn them here. And so, given a branching program of width w and length n, we can associate n w by w transition matrices, which are giving the transition probabilities from one layer to the next layer when I choose that input bit at random. So, for example, W1 would be this transition matrix, like from the first vertex, so that's column 1, I have probability half of going to the first vertex, probability half of going to the second vertex. This 1 here in the bottom means that if I start at vertex 4, I have probability 1 of going to vertex 4. So I do that for each of the n layers. And then I can make a transition matrix for the entire standard order branching program by now making a block matrix where the blocks, the first block corresponds to the first layer, the second block, I guess we have n plus 1 blocks because we have the 0th layer, first layer, second layer, and up to the nth layer. And I just put the transition matrices here. So this is the transitions from layer 0 to layer 1 to layer 2, and so on. Okay, and so these are giving the transitions. This is a sub-stochastic matrix. So the WIs have column sums of 1, but here we have column sums of 0 at the end because all walks die off in the last layer. Okay, so now the Laplacian, as I said earlier, is just identity. This is n plus 1 times w by n plus 1 times w identity matrix minus w. This is this now w of the entire, this block matrix of the entire standard order branching program. And as they mentioned in the, what they're interested in the time-bounded case, or this literature's interested is inverting Laplacian, solving Laplacian, or computing their inverses. So let's see what that gives us for our matrix W. Well, we can use the power series expansion of I minus W inverse. And that gives me, walks of length 0, walks of length 1, walks of length 2, walks of length n. And then all longer walks are 0 because of what we just said before, that all walks die off after they fall off the nth layer. So if we write this out, we get a block matrix that's quite natural to look at. So our walks of length 0 give us identities on the diagonal. If we walk from layer I and do a walk of length 0, we'll stay in layer I at the same vertex. Then we get walks of length 1 next below the diagonal. So this is just the matrix W1, but I'm writing it as, because it's going from layer 0 to layer 1, layer 1 to layer 2 to layer 3. And then I get walks of length 2, so going from 0 to 2, 1 to 3, and so on. So this W to I, I goes to J is saying I start in layer I, use Wi plus 1 to go to layer I plus 1, then I plus 2, and so on, and up to apply Wj to end up in layer J. Okay, so this is basically giving us the transition probabilities for the entire branching program for walks of all lengths. So for every 2 nodes in the branching program in different layers, it will, reading off an entry of this matrix will tell me the probability. If I have a random, uniformly random input, I'll go from that state to the other state. And in particular, if I look in the lower left block and I look at the 0th entry, or 1, I guess I was using 1, 1 before, one entry of that, that'll just exactly give me the acceptance probability of a standard order branching program, which is the, the complete problem for BPL. That's the quantity we want to compute. Okay, so yeah, for me, like inverting Laplacians was always this strange thing. Why are people interested in it? But kind of once we saw this connection, it's like, oh, this is why I should care about inverting Laplacians. All right, great. So now the first idea that I want to describe coming from that literature is this just very powerful technique of error reduction that exists for matrix inversion. So suppose I get some approximation to the inverse. So I'm going to write this L inverse tilde. All right? But maybe it's not a very good approximation. It's some kind of weak approximation. So to within, say, some constant error. And what this norm here is some submultiplicative matrix norm. Later we'll talk about different choices there. But for now, you can just think of it as the L2 operator norm. Or also called the spectral norm. And then having a 1/2 approximation. Oh, and so this is the way I want to measure how good my approximation is. So one way to say is, well, if it were the true inverse and I multiplied by L, I would get the identity out. So instead, I look at how far am I from the identity when I multiply my approximation to the inverse by L. And this condition turns out not to be good enough to read off the acceptance probability that we're interested in. Just having this constant approximation on the entire thing. But it turns out you can, from this, boost your quality of approximation very efficiently by what's called preconditioned Richardson iterations. So the true inverse that we're interested in, I can write in this way. This is really just like I take my approximation, and then I multiply by the inverse of this thing, and I will get exactly the L inverse that I'm interested in, which I can then write in a power series expansion by expanding this inverse. So in this power series, each term corresponds to raising this error matrix here by some power j. And this series, because this error matrix, we've assumed it to have bounded error in some submultiplicative matrix norm, it turns out that this series will converge very quickly. And in particular, if we truncate it at t terms, the error in my approximation inverse in this same norm will go from alpha to some alpha to the t. And so if I truncate at t being log base 1 over alpha, so alpha is a constant. Think of alpha as a constant, so log of 1 over epsilon. And then I'll put an NW here because I want to be able to switch norms and switch from this unspecified matrix norm to entry-wise approximation of that acceptance probability that I'm interested in. That will suffice to compute the true inverse entry-wise up to plus or minus epsilon error. And then the cool thing is, so they use this a lot in the time-bounded case, but it also has a very space-efficient implementation. and turns out can be implemented in space efficiency that's log NW. That we're like the standard thing we're willing to pay. There's only an additive cost in space over the cost of calculating this approximate inverse times something that's basically log in 1 over epsilon. And the reason for log is if I'm raising to powers up to this value of t. And if you do the space-efficient matrix powering, your space is the space to multiply two matrices. That's like the log NW times log of the power that you need to raise to. This is like just doing matrix powering by repeated squaring in a space-efficient recursive way. All right, so what's some mileage we got from that? Some immediate things is you can take any algorithm that approximates the acceptance probability to within polynomially small error and then get it to arbitrary epsilon, like smaller than 1 over poly, with only a log blow up with this additive, with this kind of log dependence on epsilon. So you could even apply it to the randomized algorithm for estimating the acceptance probability. You could apply this technique. And you can apply it to the Sachs-Joe algorithm, again, replacing what used to be a log 1 over epsilon space complexity in Sachs-Joe to one that has a log dependence. Okay. We're starting out with this 1 over poly accuracy. That's our before, in order to, all right, so this will typically be like some entry-wise error that you start with, and then you turn that into this matrix norm. You might pay some polynomial in that, and then you do this error reduction procedure. Right? And these match bounds that were given by Hosa and Zuckerman for RL, one-sided error, and now we can get that for two-sided error. Okay, so next, this was just kind of a first immediate application of that error reduction, but it's turned out to have lots of other applications that I want to talk about. But first, let me just give one other nice interpretation of this error matrix that came up in this analysis and has been kind of understanding this has been important in some of the other applications or improvement. So, right, we saw our Laplacian is we have identities and then minus the wi's off the diagonal, and then L inverse were these walk probabilities from layer, each layer I to layer j, and we have some approximation. So we think of the approximation as giving us approximate probability, kind of walk matrices for each pair of layers. And that's what I'm writing with these approximations with tildes. And it turns out, if you just calculate the matrix product and minus I, the blocks of that matrix are going to be of this form. Looking at the difference between, this is our approximation of walks from layer I minus 1 to j, versus doing a truly random step from I minus 1 to I, and then an approximate walk from I to j. And so if our approximations were perfect, these blocks would be 0. The error matrix would be 0. But these are known as what are called the local consistency errors introduced by Cheng and Hosa, and they're a very kind of natural thing. Somehow you have these approximations, these local consistency, given the approximations, you can kind of check very efficiently with just one kind of matrix multiplication here, which you can do space efficiently. You can very kind of efficiently check how good, verify that these are good approximations with these local consistencies. So this is kind of nice way of thinking about this weird error matrix that comes up. Okay, but the way we get an improved estimate is by this power series that raises that error matrix to some power and then multiplies that by our approximation to L inverse. And if you kind of expand things out, the form of what you get is going to look something like the following. So like a block, an IJ block in our improved estimate, because of these matrix powering and the fact the blocks of what those consist of, it's going to look like something like the following, where I have some sum over terms of coefficients that may have plus or minus signs, because I have a minus sign here, and then also in the blocks of that error matrix I have minus signs appearing. So I'll get coefficients that have plus or minus signs, and these cancellations are part of what's providing the error reduction, times a product of pseudorandom walks. Like we're going from layer I to some other layer I1, and then from that layer to I2, and so on up to layer Ij. Okay, so there would be some W's, true W's, one-step W's thrown in there. For simplicity, let's just assume that our approximation for one-step walks are the same as, are just perfect, which you can assume without lesser generality, and then this description is exact. All right, so what did I want to say about this? Suppose in the applications I talked about before, we got these approximations by using an algorithm, using like the Sachs-Joe algorithm. We got these approximations with polynomially small error. Let's move to the black box setting, where we like have a pseudo-random generator instead. We don't get to look at the algorithm. The observation is that if these matrices are coming from a pseudo-random generator, what do I mean by running, averaging our program over the seeds of a pseudo-random generator to go from layer I0 to I1, and then I1 to I2. If that's where we're getting these W tildes from, then you can interpret this quantity as what's called a weighted pseudo-random generator. It's a concept introduced by Braverman, Cohen, and Gerg, where we think of the seed of the weighted pseudo-random generator as first picking a term, so that's giving us this summation here, specifying a coefficient, that's what this is, and then specifying seeds for each of these walks, and concatenating those kind of pseudo-random outputs to say how you go from layer I0 to IK. Okay, and so what we know from the error analysis we saw, the fast convergence of the series, is that if I do this for the lower left block, going from layer 0 to layer n, this will be a low error weighted pseudo-random generator. It will approximate the true 0 to nth walks really well with high accuracy. But unfortunately, it won't have a very short seed, because we're concatenating all of these independent pseudorandom walks. We're using one pseudorandom seed to go from I0 to I1, another one to go from I1 to I2, and so on. Okay, and so the idea from this paper of Cohen, Doron, Renard, Sperlo, and Tashma, and then Ted Pine and myself, is to de-randomize these products using, well, we used the INW pseudorandom generator to de-randomize these matrix products. And then Hosa added on top another idea using an averaging sampler, and gets a weighted pseudorandom generator for general standard order branching programs, which basically in Nissan's generator, we had a log NW over epsilon here, and this just moves the dependence on epsilon outside to the optimal additive order log 1 over epsilon. And so these earlier papers, they've been in Braverman, Cohen, Gerg, and these other ones, we had O tildes either on the first term or the second term or both, and Hosa removes all those O tildes and really gets this like kind of sort of optimal error reduction for weighted pseudorandom generators. Not even needing all of these improvements, Hosa used this also, plugging these WPRGs into the Sachs-Joe algorithm, replacing Nissan's use of Nissan's generator there with weighted pseudorandom generator, gets this improved de-randomization of BPL that we mentioned. Questions? How this last thing comes? I don't have a succinct one sentence. It's some like fine tuning of parameters. I don't have a succinct answer to that. All right. The other, just last thing in this part that I want to mention, I mentioned this result of de-randomizing medium width standard order branching programs. So the previous result was kind of in the black box setting. You're generating using this weighted pseudorandom generator. You don't get to look at the program. If you move back to getting to look at the program, these two very recent papers of Cohen, Doran, Sperlo, and Tashma, and Putterman and Pine show that what you can do is instead use these preconditioned Richardson iterations, this error reduction procedure, inside the Sachs-Joe algorithm, and get a better algorithm, specifically where the space complexity is log n plus square root of log n times log w. This used to be in Sachs-Joe, this used to be a log nw. So now it's just log w here. And in particular, if your width is as big as up to 2 to the square root log n, this will be nearly logarithmic space, O tilde log n. All right, but the main thing, takeaway, one point is the relevance of inverting Laplacians to de-randomization. Like you can just read off from the inverse of the Laplacian the acceptance probability, which is the quantity we're interested in. And second is this error reduction technique. Two main ideas to take away. In this last bit, maybe just more briefly, I want to just give a little bit of a sense of how notions of spectral approximation are playing a role here already under the hood in some of the things that I've been talking about. So how do we obtain this approximate inverse, which sometimes, again, is called a preconditioner, because you're pre-multiplying L by it to get something that's better conditioned is the intuition. And we have freedom to choose this matrix norm. This error reduction works well basically as long as you have any submultiplicative matrix norm. I mean, you can make some really crazy norm where you pay some price, too big a price moving back and forth. But for kind of any reasonable norm is OK. Generally, that hasn't been an issue. So far, the way we did it was we start with a pseudorandom generator, an algorithm that has polynomially small error, and then we saw how to amplify that to much better error. Because the nice thing about when you have polynomially small error, you can move from entry-wise error to L2 operator norm error, and just use your standard operator norm as your submultiplicative matrix norm. But this is not going to beat Nissan's generator, or if we're thinking of the black box setting, if I'm starting with a pseudorandom generator that has a seed length of log n times log 1 over epsilon, and I need to take epsilon polynomially small, I'm going to still get this like log squared that Nissan has, log squared n, if I have to take epsilon polynomially small. Right? And there's several examples of generators where we have this kind of a seed length for restricted models of space-bound computation, log n times log 1 over epsilon, where we really would like to apply the same idea, but without taking epsilon polynomially small. All right, so let's understand, what do we need? What does it mean for this to hold with some submultiplicative matrix norm? This is basically equivalent, with a small amount of cheating, it's basically equivalent to every eigenvalue of this matrix, this preconditioned L, approximate inverse times L, being, this might be a complex eigenvalue, but being close to 1. To be within error alpha. Now, if and that's equivalent because of how eigenvalues kind of work under cyclic permutation of matrices, I could instead have L to the half on both sides, and that's particularly useful when the matrices are symmetric. So at least in the undirected case, where L is symmetric and the approximate inverse is symmetric, this is equivalent to our approximate inverse being an approximation to the inverse of L in the PSD, like Lohner order. which you could also take inverses again and just have the inverse of our approximate inverse being a PSD approximation of L, where this ordering, if you haven't seen it, just requires that the quadratic form defined by one matrix is less than or equal to whatever 1 plus alpha times the quadratic form of the other matrix. This definition only makes sense for symmetric matrices. These quadratic forms lose any asymmetric information that's in the matrix. So what I wanted to get to is this is exactly the Spielman-Tang notion of spectral approximation that they use for defining spectral approximation of graphs and was kind of the key to this whole literature on Laplacian solvers. And so this is where kind of eigenvalues were hiding under the hood. So how did we get our undirected Laplacian solver? We just used that notion of approximation. We modified one of the algorithms that was developed in the time-bounded case, the Peng and Spielman algorithm, to obtain our approximate inverse. That algorithm works by a repeated squaring. The algorithm works by you take your random walk matrix, you repeatedly square, and then sparsify to produce a spectral approximation, and the square again, and sparsify to get a spectral approximation of that power. That sparsification is done in a randomized nearly linear time way. To get a space-efficient algorithm, we replace it with doing an expander-based squaring, de-randomized square operation that came from kind of work that we did following Reingold's algorithm. So like you're doing this repeated squaring, and your kind of jth repeated square, approximation of the jth repeated square, is a spectral approximation to the true square of your j minus 1th approximate square, is the property that we need. And then the other key property that we already knew about this de-randomized square operation, it's similar to the space complexity analysis of Reingold's algorithm, even a little bit simpler, is that you can construct these approximate squares in time O of log n plus j times log of 1 over alpha, where alpha is your kind of your level of approximation we're looking for. And this is like winning over true squaring. Like if you just do true squaring, repeated squaring, you'd have j times log n. If you square j times and each time pay a log n in your space. So that's the win here. I think I'll skip for sake of time. When you do a true square, you get lots of cliques, and basically these cliques are all replaced with expanders, and we have to show that in what we previously knew 15 years ago, is that this de-randomized square operates on the second eigenvalue, on spectral expansion, similarly to the true square. What we now know is that it actually has this stronger notion of approximation of spectral approximation. And it's a very kind of easy proof, and it has to do with really this very nice properties of spectral approximation, that it's additive if you do something locally on all the parts of the graph. As long as locally you're doing spectral approximation, because it's this multiplicative relative notion of approximation, you immediately deduce that it holds globally on the entire graph. Okay, so just want to mention that unfortunately, if we think of our application to branching programs, log space, these matrices are kind of very directed, right? Branching programs are very directed, very asymmetric. And even if you're thinking of the branching program that corresponds to doing random walks on an undirected graph, so every WI is the same, they are all corresponding to one step of a random walk on an undirected graph, this matrix that we construct from it is still going to be this lower triangular, lower diagonal asymmetric matrix. And so we really need to work with ideas that work well with directed graphs. And so, as I mentioned, the time-bounded literature had developed such notions. We don't know how to implement those algorithms kind of as is in deterministic nearly logarithmic space, but we take some ideas from there. And then had to introduce some new notions of approximation that we called unit circle approximation and singular value approximation. New notions for directed graphs that had some other nice properties, like when you do powering, you basically pay no loss in your level of approximation. If I have a random walk matrix U that approximates to within alpha random walk matrix V, or their Laplacians approximate in these new notions, the kth powers also approximate with no blow up depending on k. This was used in the pseudorandom generator for, that I mentioned, for unbounded width permutation programs. And it's turned out these notions are also useful for new algorithms in the time-bounded case. All right, so let me skip over, as again, the exact results are less important. I just want to mention there's this really, and a lot of actually the perspective that I've been taking in the talk is coming from this new paper that I just got a draft of last week from Chen, Hoza, Liu, Tal, and Wu, which really gives a kind of nice holistic picture of all of these ingredients and how they fit together. There's still a lot of sort of sophistication, it seems, going into how do you figure out the right norm to measure error in to be able to carry out this approach. But doing that, they get new weighted pseudorandom generators for these three models that I mentioned. Previously, we had pseudorandom generators with log n times log 1 over epsilon, and they're getting log n times square root of log 1 over epsilon. And choosing different norms in each case. So in the case of permutation branching programs, it's some PSD norm that's related to this concept of singular value approximation that I mentioned. And in the other two cases, they're using an L infinity operator norm. All right, so I have lots to say about research directions, but I'll keep it short. We can talk over lunch. All right, so if you want to, really, of course, what we want to do is get BPL in deterministic log to the C for some C less than 3/2. There's two ways you can tackle it. You can tackle it in the algorithmic case, the white box case, where you get to see the branching program. Currently, our state of the art is these results are medium width programs, but when the width is polynomial, you still get log to the 3/2. All right, so that's what we want to beat. Or it would suffice to improve things in the black box, like the pseudorandomness setting, where you don't get to look at the program. And there, our state of the art is like a log n times log w. And there, you could even just work with regular. Even for regular programs, our best is like log n times log w. And again, if we can improve this polynomially, we would improve de-randomization of BPL. And then the other idea is there a good way to combine this collection of ideas with another set of approaches that has been getting a fair amount of mileage in de-randomizing restricted classes of space-bounded computation, which is the iterated pseudorandom restrictions approach, which didn't say anything about in this talk because it's not. I wanted to focus on the spectral approach, but they feel like they are, and there's even some formal sense in which they are good for sort of opposite ends of the space-bounded branching program spectrum. And if we could only find a way to use them at once, it feels like we should be able to get a better end result. All right, and let me omit all the details that are here. And then I just want to mention they're also more open-ended, like research directions, a lot of which I think are interesting, not just in our space-bounded setting, but also back in the time-bounded setting. Already, some of the ideas that we've been developing in the space-bounded complexity theorists have been developing have been useful for solving new algorithmic problems. And it might be nice for more of us to turn our attention to some of those algorithmic problems. And in particular, I think there's also, Tim was asking me this question yesterday, there are also some open de-randomization questions about getting deterministic nearly linear time algorithms for some of the problems where they have randomized nearly linear time algorithms. So let me stop there. Yeah, so I didn't get to talk in too much detail about it. So the kind of the error matrix and our approximate inverse has these terms that are like in our existing constructions of these preconditioners. They have terms that are coming from these like repeated approximate powering algorithms. So we have these matrices that satisfy those kinds of notions of approximation that I was talking about, like in the undirected case, like the Spielman-Tongue notion of PSD approximation, or these new notions for directed graphs. But then we're building this complicated block matrix out of them and looking at the error matrix that's induced by that big block matrix, that's the pseudo-inverse. And we need to figure out what matrix norm on that can we bound the error of that overall thing. And it's still a bit of a mystery. When we did it in the AKM-PSV paper, we were like importing lemmas from the Laplacian solving literature that were kind of seemed like magic to me that I still don't have a lot of intuition for. I think this new paper of Chen et al. Has made some good headway in unpacking what's going on in those. But there's still, I think, a lot more to understand and hopefully simplify there as well. In the undirected case, it's very, very simple. It turns out that just having normal PSD approximation for these, for the way that you construct the approximate inverse, the preconditioner, you get the normal just PSD approximation for your approximate inverse. And there's no magic norm that's kind of chosen.
And then the spectral norm is fine, right? Because you just have like that.
So I guess if you have PSD approximation, it implies not in the spectral norm, but in some PSD norm that might be like related to the Laplacian. But it's like a standard thing. It's very easy to kind of extract from that a submultiplicative norm. Yeah. Pierre.
So Salil, if we think back to Barrington and Denier, who studied permutations versus aperiodic monoids and stuff like that, does it make sense to talk about aperiodic branching programs in this setting?
Remind me, what's an aperiodic branching program?
It's the opposite of a permutation. So you don't have groups around. It's like in a semigroup, take a semigroup that has no non-trivial group in it.
Oh, I mean, it seems like it might be worth looking at. I mean, so this opposite model I was referring to is in a paper with Dean and Avishai and Raghu and Omer called monotone branching programs, where we were trying to like formulate what seems to be the opposite of the permutation. But maybe we should look at this kind of concept of aperiodic and see if that gives us a different or kind of more general negation of the permutation property.
So perhaps a very high-level question. You spoke about magic, and in some sense, I always felt a bit there's something mysterious about spectral graph theory. I mean, we start with a graph as a purely combinatorial object, and then, for convenience, we need to represent it, so we write it in a two-dimensional array. Then it's already a two-dimensional array, so we view it as a matrix. But then suddenly, you view this matrix, and then suddenly it's a linear transformation. suddenly it captures expansion. Or you can talk about, standard order branching program that captures the accepted probability. So I guess I'm asking if you have any nice intuition as to where this linear structure of graphs, or where is this all coming from? I mean, each one of these proofs by itself, I can understand how they work, but I have no intuition about where linearity actually lies.
Yeah, as I indicated in my comments, there certainly are still parts of spectral graph theory, of even the small subset of spectral graph theory that I've learned, small parts of it that are like magic. There's still some parts of it that are magic to me. But the things that I personally kind of hang on to for intuition is really thinking in terms of random walks, and kind of once comfortable of thinking of the kind of random walks being represented linear algebraically, I try to connect everything to that. That the powering of the stochastic matrix is giving you longer random walks. I know others who work in this space really prefer, in terms of intuition, to think of these as fractional relaxations of like cut problems. This is like what Tim was mentioning earlier, that if you think of, all right, I have this thing, in the undirected case, for example, I think of the matrix as defining a quadratic form. But if I think of that as just like plugging in into like 0, 1 vectors, it's exactly giving me values of cuts, how many edges are crossing cuts in the graph. And then this is this fractional relaxation. But there's still the step there. Okay, now once I do this fractional relaxation, I all of a sudden have all this machinery of linear algebra to apply, and that does seem to give some magic. But I think finding whichever one of these or other, some combinatorial intuition to hold onto and kind of reinterpret everything you see in that intuition, at least has been my strategy for navigating this toolkit.